Study Section 14, ANOVA One-Way Classification. Introduction. The basic ideal of analysis of variance is to express a measure of the total variability of a set of data as a sum of terms, each of which can be attributed to a specific source or cause of variation. The observations in the sample data may be classified according to one-factor criterion or two factors criteria. The classifications according to one factor and two factors are called one-way classification and two-way classification respectively. We shall consider the former in this study section. Learning outcomes for study section 14. When you have studied this session, you should be able to understand the layout of one-way classification, construct ANOVA for one-way classification, and test hypotheses for the equality of three or more population means. The layout of one-way classification. Suppose that there are k treatments, j is equal to 1 to k, and that treatment j has nj observations. Xij is the ith observation on the jth treatment. The observations measurement obtained for k independent samples based on one criterion classification can be arranged as shown in the following table, where Tj is equal to is called the treatment or sample totals. T is equal to is called the grand total of all observations or measurements. X bar j is equal to is called the treatment or sample means. X double bar is equal to is called the grand mean of all observations or measurements. Since there are r rows and k columns, then total number of observations is rk is equal to n, provided each row has equal number of observations. But if the number of observations in each column varies, then the total number of observations is n1 plus n2 plus nk is equal to n. Steps of constructing the ANOVA. Step 1. Calculate the total variation. The total variation is represented by the sum of squares total, SST, and is equal to the sum of the squared differences between each sample value from the grand mean. SST is equal to Step 2. Calculate the variation between sample means. This is usually called the sum of squares between SSB. It measures the variation between samples due to treatments. In statistical terms, variation between samples means is also called the between-column variance. SSB is equal to Step 3. Calculate the variation within samples. This is usually called the sum of squares within SSW. It measures the difference within samples due to chance error. Such variation is also called within sample variance or error sum of squares. SSW is equal to, alternatively, SSW is equal to SST minus SSB. Step 4. Calculate the average variation between and within samples, mean squares. Since k independent samples have been compared, therefore k-1 degrees of freedom are associated with SSB. Also, as each of the k samples contributes nj minus 1 degrees of freedom for each independent sample within itself, therefore there are n minus k degrees of freedom associated with SSW. Thus, total degrees of freedom equal to the degrees of freedom associated with SSB and SSW. That is, when this sum of squares are divided by their associated degrees of freedom, we get the following variances or mean square terms. MSB is equal to SSB over k-1. MSW is equal to SSW over n minus k. Step 5. Compute the F statistic. The F statistic is given by F is equal to variance between over variance within is equal to the following table shows the general arrangement of the ANOVA table for one factor analysis of variance. ANOVA summary table. Testing for the equality of population means. Hypothesis. Decision rule. Reject H0 if the calculated value of f is greater than its critical value f alpha into bracket k minus 1 n minus k bracket closed. Otherwise, accept H0. Note: the F distribution is a family of distributions each identified by a pair of degrees of freedom. The first number refers to the number of degrees of freedom in the numerator of the F ratio, and the second refers to the number of degrees of freedom in the denominator. In the F table, columns represent the degrees of freedom for the numerator and the row represents the degrees of freedom for the denominator. Example: there are 5 treatments A, B, C, D, and E for lowering blood pressure. An initial test is needed to ascertain whether there is any real difference between them. Each treatment is given to a different randomly chosen sample of people with high blood pressure. The results using C-table units are as follows. Test at 5% level of significance. Whatever the different treatments has the same mean effect. Solution. Hypothesis. H0 such that the means of the treatments are equal. H1 such that the means of the treatments are not all equal. Computations. For this data, k is equal to 5, n1 is equal to 5, n2 is equal to 7, n3 is equal to 6, n4 is equal to 4, n5 is equal to 5, and n is equal to 27. The treatment means are S1 bar is equal to 8, x2 bar is equal to 13, x3 bar is equal to 4, x4 bar is equal to 8, x5 bar is equal to 19. The grand mean is x double bar is equal to 10.44. Within samples, sum of squares SSW is equal to 370, degrees of freedom n minus k is equal to 22, mean squares MSW is equal to 16.82. Between samples, sum of squares SSB is equal to 738.6, degrees of freedom k minus 1 is equal to 4, mean square MSB is equal to 184.6. The test statistic F is equal to 184.6 over 16.82 is equal to 11.00. ANOVA table. Source of variation, sum of squares, degrees of freedom, mean squares, test statistic or F value. Between samples, within samples, total. Decision. The critical value for F for 22 at the 5% significance level is 2.82. Since 11.0 is greater than 2.82, the null hypothesis is rejected. The different treatments do not have the same mean effect.